We introduce a new formulation for procedural noise generation. In this first example, the texture is entirely described by 36 numbers. The noise is computed on the fly in a pixel shader. Color is obtained by feeding our noise into a simple color map shown as an inset. This procedurally generated isosurface is textured on the fly by our procedural shader. No precomputation is required, hence the surface may be dynamically modified and can even sustain topology changes. Since everything is being computed on the fly, the user may change the noise interactively at any time. This is our interface for interactive noise design. On the left, the spectrum of noise, the color map, and the grayscale noise pattern. The noise spectrum is directly controlled through a simple widget. The user manipulates natural noise parameters such as frequency or orientation. The user can also control the angular and frequency spread. The computed noise spectrum is shown below the widget. Notice how well the noise we produce matches user input. More widgets can be added to produce more complex patterns. Each adds its own contribution to the noise. The texture can then be applied to any object. The core component of our noise is the Gabor kernel. A key property of Gabor kernels is that their Fourier transform is a Gaussian and its symmetric counterpart. By changing the parameters of the kernel, this Gaussian may be positioned arbitrarily in the spectrum. We obtain the noise pattern by using Gabor kernels in a sparse convolution process. Kernels are spread at random locations in the plane. With a high enough density, a noise pattern is obtained. It has the spectrum of the kernel. In addition, by splatting Gabor kernels with varying parameters, a more complex spectrum is obtained. Here, we randomly choose the orientation of the kernels. The resulting noise is isotropic. Please refer to the paper for analytical derivations. The widget directly controls the parameters of the Gabor kernels, such as frequency, bandwidth, orientation. It is also used to specify how these parameters vary during sparse convolution. Here, a random angular spread and a random frequency spread. This enables continuous control from anisotropic to isotropic patterns. We define noise on surfaces by splatting kernels along the objects. Everything is done from a pixel shader. The noise is anisotropically filtered. Our noise formulation trivially generalizes to 3D for solid texturing. Solid textures give the unique feeling that the objects have been carved out of blocks of matter. However, this is not always what is desired. Here, the user would like the fibers to follow the surface, but instead, an anisotropic solid noise changes aspect with surface angle. Using our on-surface noise definition, the pattern remains the same everywhere. Yet, no precomputation is required, and no texture coordinates need to be specified. Thanks to direct spectral control, we easily create a variety of patterns. A simple color map is enough to obtain interesting and complex textures. Our noise formulation combines all advantages of previous approaches. It is procedural, 2D, 3D, and defined on surfaces. The noise spectrum is precisely controlled, enabling high-quality filtering. Any object can be immediately textured without precomputation or texture coordinates. We believe it will find many applications in graphics as well as in other areas.